Hey guys, Math 6620. Going to put up a video here on multiple regression and run through some code on R, look at some diagnostics, and just get into some stuff. Kind of a cool video, I think, if I do my part right. Guys, there's a data set read district. It's already in .csv format that we need to get into R. So I'll tell you what, let's go ahead and do that. I should have already had this done, but I don't. So I'll tell you what, I don't remember. Okay, that's what I thought. Usually work on another computer, but this is going to be fine. So guys, let's go get our data. Not sure why I capitalized everything, but I did. Now, what we got here, we have some scores on some grade school kids. And we have read, which is a quantitative variable, LSS, which is quantitative, IQ, obviously quantitative. Estimate, this is an estimated reading level. Gender is categorical, dichotomous, and school district. I think there's 4 school districts, A, B, and C. So, guys, I think the first thing I'd want to do is define what kind of model we want to create here, and I want to be able to predict read from all the other variables. So, guys, I'm going to give my model a name and run LM, and I want read as a function of the other variables. Now, let me back up a little bit. School district. If you go to the Excel spreadsheet, you'll see that we have A, B, C, and D. Now, in the previous video, I talked about setting up dummy variables. And now with gender is categorical, but because it's dichotomous, has only 2 groups, you can set the default either by changing these to 0s and 1s, as I've demonstrated in a previous video, where 0 is the base and 1 is 0 is the comparison group, and the 1 is the group that will be compared to the comparison group. But with school district, we have 4 school districts here, A, B, C, and D. So in this case, whatever the first school district is, whatever the first level of a categorical variable, speaking more in general, whatever that is, that will be the base group. Now, if we wanted to, for some reason, to have D as the base group, all we would have to do is just come in and maybe cut this out and insert it there to where the first school district was D. So anyway, it's a little wacky the way it does it, but it's easily manipulated to set the first school, in this case, as the comparison group. But guys, the data set that I imported into R had school district A as the comparison group. So guys, let's make it happen here. Let's run a little bit about run our model. So first thing I'd want to do is summary of my model, and for what we're looking for, we typically have tunnel vision for the last column, the probabilities, the p-values, and we can see that although not statistically significant at the 0.05 level, EST is significant at the 0.10 level. Now, we would also want to get into our model diagnostics. So to do that, I would run an ANOVA of our model. Now, I tell you, I don't like the way that R does this for the ANOVA, because you would typically want just one line for your model and then one line for your residuals. But guys, from things that I've taught you before, we know that the sum of squares are additive, so we could add these 4 sum of squares. Mean square are not additive, but we can take the degrees of freedom, which are additive. So, okay, anyway, long story short, I could come up with the mean square for the regression by taking the sum of squares for the regression, which would be all four of these numbers, divided by, in this case, the sum of the degrees of freedom, which would be 4. So I could therefore create the mean square for the residual and for the regression, easily calculating a p-value for the F statistic. And that's going to be a homework assignment that I'm going to have you do. So again, previous videos I've illustrated things like that. All right, let's get into a couple more things. If I wanted to do confidence intervals, which this is going back to the coefficients, if I'm looking at the coefficients and not the overall model, I could do the confidence intervals for the predictors just by doing model and setting the level at the desired level, and I would just do 0.95. Now, when you look at the confidence intervals, remember the null hypothesis here is that the beta sub I, so the parameter value for LSS, the parameter value for IQ, the parameter for EST, and the parameter for gender is equal to 0. So if we look at a confidence interval and it contains 0, which clearly if the left bound is negative and the right bound of the interval is positive, then it contains 0. So we do not have statistical significance at the 0.95 level of any, the 0.05 level from the 95% confidence interval. However, you'll notice that if I change the confidence level to 0.90, we did see at the 0.10 level that we did have statistical significance for EST, right? Yeah. Now, don't get confused with the ANOVA values versus the coefficients. These ANOVA, this is only useful to us when these values are actually combined. Okay? So, we can see at the 0.90 level that we get a confidence interval that doesn't contain 0. So because the confidence level was 0.90, this tells us that EST is statistically significant at the 0.10 level. So that's the way that we get the confidence intervals, which is something that you would report when reporting multiple regression in ed research. The next thing we'd want to look at, I want to look at the variance covariance matrix. Let's just look at the covariance matrix. So to do that, we would do VCOV, and then the name of the model, which in this case is just model. And what we typically look at there, first of all, we notice that we have a symmetric matrix, and it's closely related to the correlation matrix. But the difference is the covariances, which are just unstandardized correlations, are presented here instead of the correlations. So it's kind of the covariance is an unstandardized version of the correlation matrix. And I demonstrated a correlation matrix about a week ago when we were looking at correlation. Now, one thing to think about here is, I think I'm just going to leave it at that. Guys, let's go into influence statistics. So what we do with influence statistics is we look at ways to determine cases or potentially variables that just exert a lot. I was going to say significant influence, but I don't want you to think statistically significant, but just have a lot of influence on our model. So this is a good place to start with that, the influence model. And what you'll see is we get dollar sign hat, dollar sign coefficients, dollar sign sigma, and some weighted residuals. So let me go through and tell you what these things represent. The dollar sign hat, these are actually in the hat matrix. This is actually a vector, and you can see that we have 30 of them, which corresponds to the number of cases. So if we were to do, I don't think we've talked about the hat matrix, have we? Let me, I'm getting the cart in front of the horse here. Let me back up a little bit and tell you a little bit about the hat matrix. The hat matrix plays a special role in matrix operations on performing multiple regression techniques. And what we can see is, and if you take 5500 and 6500 from me, you'll see this ad nauseum. But we can see that we can find the predicted y's by taking the product of these matrices. Now, just to give you an example, this Y matrix is nothing more than the Y's for the, in this case, the data set that we're looking at for the 30 observations. So, you know, whatever the Y's are, this would be the Y matrix. The X matrix is the coefficient matrix, and then we look at the transpose and inverse. But again, that's for another day when you take 5500 from me. Well, it turns out that this matrix right here, this product matrix, which you can see would be H times Y, can be seen of as kind of a projection matrix. In other words, it's the matrix that maps our Y's onto the predicted Y's. So this H again is kind of seen as a projection matrix, and it's symmetric. And these diagonal values tell us some cool things about the influence on the cases. Okay, so we ultimately have a 30 by 30 matrix. So we have a diagonal of 30 units, and that is what. Let me go back to R. That's what you're seeing right here. So these 30 numbers that I've just highlighted would be the where are we? Okay, would be the numbers that would be right here. And what this does, Stevens, we observe these to see if there are any high values. Now, what's high? Stevens at the University of Cincinnati says that we have, I think it's 3 times k plus 1 over n. So in our situation, you know, k is the number of predictors, so I think we had 4. So 3 times 5 is 15 over our sample size of 30. So we can see here 15 over 30 is 0.5. So guys, if we have any value here that's over 0.5, then we have a case that is exerting more than its influence on our model. So the highest value that I see there is 0.32, which is the 5th case. So let's see what's up with the 5th case. Although it's not of concern, well, guys, I messed with that, didn't I? So the 5th case would be in the 6th place. So this person right here, male with an IQ of 89, which is one of the lower IQs, other than this one at 82. But anyway, this particular person has a lot of influence on our model, but not so much that we're concerned about it. The next thing are the dollar sign coefficients. This is this provides the coefficients if the ith person is deleted. So you'll see we have 30. So for example, if we come in and delete this 5th person from our data analysis and rerun our multiple regression, then the intercept would go from negative 28.40, well, 0.50 to 1.98. The LSS would change to negative 0.07 from 2.63. So you go through here and you can look to see the impact on each of these, deletion of each of these people on the overall diagnostics. $ sigma is just another vector where the ith element estimates the standard deviation of the residuals if the case is dropped. So if we come up, part of our output on the coefficient output is the residual standard error. So we can see we have degrees of freedom 25. Residual standard error, think of that as like the standard deviation of the residuals, 18.84. So when we come down here, we can see that I eyeball these. I don't really see a drastic change. It does look like case number 20 drops, the variation decreases quite a bit. So that may be something in your write-up that you would want to point out. I wouldn't throw the baby out the bathwater here and delete number 20, case number 20, but I would want to report that the standard, the residual standard error does decrease when that case would be deleted. Guys, the weighted residuals, I don't do much with this, so I'm going to just ignore that at this time, okay? Next thing we get into is we get into some graphs, and R really has kind of a cool function here. It gives you some pretty cool cool graphs just by typing plot for a model, and I think it'll bring up 4 plots. Alright, why is that not working? Huh, guys, that's always worked for me. So, okay, here we go. I don't know why it... Okay, so anyway, the first plot that we have is the residual versus leverage. What I look at there is there's something called Cook's distance, and you can see that the Cook's distance is denoted by the red dashed line, and what it does is here it gives you the cutoffs at 0.5. So if we had anything up in here, we would have a Cook's of 0.5 or higher, and anything down in here we would have Cook's 0.5 or lower. But to me, at least the way I was taught, the real concern comes when we have Cook's distance of 1 or greater. Now, what this does is it measures the overall influence of a case on the model, and when I get through scanning through all the plots, I'll show you how we can also do that, just creating the vector of Cook's distance. The next thing that we get is, this is kind of clumsy. It's usually not like that. The next thing we get are the residuals versus the fitted. Guys, this is, you should never, ever, ever conduct a multiple regression without reporting this plot. What you do look for there is you look for 3 things. First of all, the residuals versus fitted plot gives us indication of whether or not linearity has been violated. What we look for there is around this horizontal line, we look for kind of a bouncing effect where we have randomness of our points. We don't want to see any U-shape or any sort of pattern of the residuals versus the fitted value. We want kind of a shotgun blast. And I think for the most part we have that there. So when I look at this, again, I look for the bouncing, the kind of random bouncing around this horizontal line at a residual equal to 0. The next thing it allows us to do is it allows us to look at unequal variances, the homogeneity of variance assumption. And what I'll do there is I come in at each level and I just look to see if the spread across each of these levels tends to be the same. So I kind of want a horizontal band, if you will. Imagine drawing kind of an ellipse here. And I want the height of the ellipse to be pretty close across all levels. So again, I read from left to right, and I just want the up and down to be pretty much the same across the spectrum. And what that tells me is that that the variance of error terms is equal, which again is another assumption. The third assumption, we look for outliers. I have some concerns with cases 20 and 21. So when I go to well, let me get rid of that. When I go to 20 and 21, these guys right here, well, one's a female, one's a male, from school district C. I may want to rerun my model with those two deleted and report the results, and let the person who's reading the results kind of make up their mind on how influential those two cases are right there. So again, the influential statistics that I'm showing you right now look at the cases. So guys, next thing, let's go on to the final one, the fourth one. And this is the normal QQ plot. This assesses normality. And this line right here is, think of it as, the y equal x line. And you can see it passes through -1, and 0, 0. And the less deviation from that line indicates that we are satisfying the normality. Now, if we get something that, has a lot of movement away from the line, then normality could be an issue with one of the predictors. But I don't see anything here that causes any problems. All right, so I'm wrong. One more. This is the scale location. The scale location is just another way to take a look at equal variances. So we want, ultimately, we want this line, this red line, to be horizontal. So considering, again, this is sample data, this red line doesn't deviate much from a horizontal line. And again, we want, across levels, we want this deviation from that red line to be mostly equal. Again, we're dealing with sample data. We don't have these theoretical, these nice classic textbook examples where everything turns out right. This is actually data that has been collected, and we always deviate a little bit from the textbook examples. So I really don't see much concern here with going ahead and running the diagnostics. I would feel, pretty, I guess, reasonably safe to use this model to predict the reading score. Now, next thing I want to look at is how we compare. No, I backed that up. I actually told you that I wanted to look at at Cook's distance and actually create the vector for you. So guys, that's easily done. It's just Cook's distance of our model. And again, you can see the vector. And, we typically have concern if any of these are over 1. So you can just eyeball it and see that everything's in scientific notation. So it looks like that no Cook's distances are greater than 1. And again, this is something you'd want to report to assure that you have checked your model diagnostics. All right, guys, I'm kind of losing my place because I really don't have a place. I'm just kind of shooting from the hip on this. One other thing that I would want to bring in is called variance inflation factors, VIF. And guys, when I start something with a hashtag, it's just I'm communicating to you. Variance inflation factors tell us about multicollinearity, and it points out whether we possibly have predictors that are highly correlated. You know, if I was trying to predict, let's say I have a group of students here at Shawnee State who I have an ACT score and an SAT score. Well, there's reason to believe, because these two tests, even though they claim to do drastically different things, they really we really expect the scores on those two exams to be pretty highly correlated across students. So you know, if I used SAT and ACT in a model to predict maybe first year GPA, because these two variables are so highly correlated, so strongly correlated, I would get a high variance inflation factor. A high variance inflation factor just tells me that I have two variables that are highly correlated, and therefore I should consider eliminating one of them because the source of information in the two is virtually identical, or highly correlated. Turns out to run VIF, you have to install the CAR package. I'm pretty sure I've already done that here, so I'm just going to access the library. Okay, warning, so we'll see what happens. And I want the VIF of my model, and you can see that my VIFs are all in the 1.0 to 1, well, the 1.0 to 2.0 range. So I'm not concerned with any multicollinearity or high correlation between my predictor variables. So now the next thing I may want to do is I may want to compare models. And let's say, for example, I wonder from this model up here, I wonder if getting rid of gender. Now wait a minute, I'm sorry, I'm not at the right one. Let's go to, I'll tell you what, let's go down here and just do a summary of the model so I get my coefficients. Now I look at gender, which in this case is comparing males to females, okay? And it has the highest p-value, so I wonder if getting rid of gender will improve my model. So what I may want to do is come down and create a second model. So I'm going to go up and get my first model. All right, and I'm going to delete gender. And I'm just going to call this model 2. And then I want to do summary of model 2. Now when I do summary of model 2, you can see that EST became statistically significant, which is fine and dandy, but I want an overall statement about the comparison of the two models. Now one thing I can do is I can take my AIC for model 1, and I can take my AIC of model 2. Now, guys, what did I teach you in an earlier video? If the AIC decreases, then model 2 is better. So if I get an AIC for model 2 that's below 267.8358, then I can say with some level of confidence that model 2 is an improvement. So it decreased, so model 2 does appear to be an improvement on predicting reading score. Another way to do that is to use the ANOVA command and compare model and model 2. Now this is a little better, or at least, I don't know whether it's better, but at least kind of validates, if you will, the comparison of AIC, because it will actually give you a p-value. So in this situation we get contradicting results. Even though the AIC decreased a couple of units statistically, in terms of statistical significance, model 2 is no better than model 1. So if we get a p-value here less than 0.05, then the second model is an improvement over the first model. So this is where statistics gets fuzzy, depending on which story you want to tell. Would be dependent upon which diagnostic that you want to report, and an AIC of decreasing only about 2 units, 1.9 actually, certainly isn't that much. But I just want you to be aware of the things that we have to do in terms of supporting the use of an improved model, or at least validating that a model is an improvement. Now, one thing I want to end on is stepwise regression. I'm not a fan of stepwise regression. No, okay, let me back up. I want to run a third model. But guys, this time I want to put in school district. And from the previous video that I posted on using categorical variables with more than 2 levels as a predictor, you know that we must do dummy variables. So I'll tell you what, let me go, I forgot actually what I called that. Okay, so if I go up and take my original model, it's up there someplace. All right, and I'm going to call this just model 3. But now I want to insert school district. This is really kind of a cool thing, because I can just put in school district and it will set as the comparison group school district A. So now I'll do summary of model 3. And you can see that it gives me, instead of just an additional predictor, it gave me the number of levels minus 1 additional predictors. So in other words, because I have 4 districts, A, B, C, it creates an extra variable that compares B to A, C to A, and D to A. So, again, if you want to, if you some reason you would prefer that school district D is your comparison group, then the easiest way to do that is just manipulate your Excel .csv file and put school district D first. So it's kind of a clever thing that R does that keeps you from setting up manually a bunch of dummy variables, zeros and ones. But anyway, guys, in analyzing this data, we can see that none of the comparisons, B to A, C to A, or D to A, are statistically significant. Now, what a lot of people like to do is they like to go fishing, and they've got this data set, and they would like to find the model that R says is the best. Now, I'll tell you right now, I don't like this. I don't like letting a computer make our decisions. I'm much more a fan of establishing a theoretical framework, doing your research questions, and using R, using data analysis, statistical techniques to address your hypotheses. But some people like to go fishing, and it turns out if you like to go fishing, well, R has a tool for you. So I'm going to call this my backward model, and I'm going to use the step function, and I'm going to start with the model, which is model 3, that includes all of the predictors. So what it's going to do is it's going to use an algorithm, use the AIC stopping criteria, and it's going to go in here and it's going to probably delete LSS first because it has the highest p-value. It's going to reassess the model, use inference, and keep going until the stopping criteria is satisfied. So guys, to pull this off, I have model 3, and I want the direction to be equal to backward. And I always turn off the trace, because really all I care about is just what I start with and what I end up with. So if I do that and just do summary backward, what it does is it tells me that the best model for predicting read, again based on this stopping criteria that R uses, is to use the IQ and EST, the estimated reading score. Guys, I think that's it. I will tell you that in terms of model diagnostics, there are lots of other things out there. I usually don't get into those here, but put on your radar. There are things called DF fits and DF betas. DF fit, think fit, right? Compares predicted values, so it'll go through and eliminate the case, reconstruct the model, and compare the residual of that case with the case of the full model. So in other words, if I have, for example, here I have, well, I think I've accidentally deleted something, but yeah, I know I have 30, so yeah, I've accidentally deleted something because I only have 29 here. But anyway, the data set that I have in R is what really matters. So if I come in, for example, and eliminate this 20th case. Now, with the full model, this case right here has a fitted value. But when I delete this case and rerun the model and then put this case into the new model that was created without that case, I can look at that difference and I get what's called a DF fit. Another thing closely related is called a DF beta. And again, what it does, it gets the model gives you the model coefficients, and it will come in and delete a case, redo the model coefficients, and with that case eliminated, and it'll compare the two results. So, guys, I think that's all I've got. I think I'm going to be teaching 5500 coming up next academic year, so you guys may or may not be taking that with me, but 5500 and 6500 is where I get into what I call the really cool stuff for multiple regression. But the purpose of this class is just to get you aware of what multiple regression does in terms of education research, when you use it. And again, when would you use it? Well, when you're wanting to predict a dependent variable that is quantitative. If your dependent variable is dichotomous, true or false, this or that, then you use logistic regression. So that's the focus here. And when it comes time to actually run one of these, that's when you dive in and look more about case-wise diagnostics and model diagnostics and things of that nature. All right, gang. I feel like I'm forgetting something, but I think I'm done. So hope you're doing well. Take care.